I'm going to skip all the introductions to QPEs and present the model that we were, me and Elliot were working on in the summer of 2022. Time flies, it's like some time, and some of them, some of those are the old thoughts, and then some new thoughts in here. So these are the typical cases of a QPE with like a 10-hour period and then duty cycle of 10% roughly. Gonna no longer need to mention the introduction, but I want to mention that the temperature of the quiescent emission is typically cooler than the eruptions. So you can see that for this particular case, during the eruption, the temperature is about 0.2 keV, and then during quiescence, it's about 0.1 keV. So slightly cooler. And this is similar to TDE thermal part, and this is hotter than typical TDEs. No UV. Okay. So I'm going to give a brief summary about the observations. Typical luminosity is the time average luminosity if you only account for the flares. During each of the flares is roughly 10 to 43, but the duty cycle is 10%, so the average luminosity. So that's the energetics to keep in mind. And these are most likely powered by supermassive black holes, many reasons for that, and perhaps low mass. Energy per flare, a typical one, number to keep in mind, 10 to 46 ergs. It's small compared to solar mass energetics. Okay. And then there's quiescent emission, a little colder than the eruptions. Nowadays, the period actually spans a wide range, but I'm still focusing on the typical one that, let's say 10 hours-ish. So these two will relate to kind of the formation channel, which I perhaps won't have the time to go into. I will try to focus on the rest of it. So there are many, many models. Actually, the time when we entered the game and after we published our model, there are still further models, and then they form into these the two big categories. So just an isolated disk, black hole disk system, and then star orbiting a supermassive black hole. But the star can be in many ways. Can have one star or two, and then you can have different types of stars. So just for simplicity, we think it's the simplest case of a main sequence star, and there's only one main sequence star. Otherwise, it becomes a little more involved. We have not thought too much more carefully about the other cases. They are still possible. Okay. So assuming that it's a main sequence star around a supermassive black hole, what are the general constraints on the system we can get? So let's say you take a typical case of a half solar mass star, a typical star, on an orbital period that's of the order 10 hours around a supermassive black hole. You require that the tidal force of the black hole would not disrupt the star. Okay, so at this the star holds itself up. So from the period, you can immediately estimate what the semi-major axis is. So depending on the mass of the black hole, it's about 100 Rg. Okay, very close to the supermassive black hole. And the pericenter has to be sufficiently far away from the black hole for the star to survive. Okay, so you can immediately know that these are mildly eccentric orbits. So the QPEs with short periods of order 10 hours, they have mildly eccentric orbits. Whereas for those 20 days or even 100-day, those QPEs, possibly then the semi-major axis could be much larger. Then highly eccentric orbits are allowed. And then one can easily do an estimate on how long does it take for the orbit to decay, right? It's of the order of mega years. So it's relatively long compared to the lifetime of the system that we know. So you take the energy budget of the system. Let's say you take a solar mass-ish star, let's say efficiency of 10%, that's the best you can do. And then you divide it by the QPE luminosity, you get something like 10 to the 1,000 years. So you know that the star will be destroyed. The system will be gone within less than 1,000 years. And the orbit will stay there. So something happens to the star that destroys the star. So we think the star should be losing mass. So this time scale is not set by gravitational wave orbital decay, and it's set by the mass loss from the star. And the mass loss of the star, again, is not driven by gravitational wave orbital motion. It's something else that's causing the star to lose mass in these systems. Another thing you immediately know is that suppose there's some gas around here. Let's say the star donates some mass, loses some mass. The accretion time, the time scale that it takes for the gas, let's say if you deposit some gas, let's say near the pericenter or semi-major axis scale, 100 Rg, it takes much longer time that's much longer than the orbital period for that gas to get accreted. So we know that eruptions, which last for 10% of the period, should not be powered by accretion. So something else is going on. So what powers the eruptions in the high states and then the quiescent emission in the low state? So let's think about the following case. Each orbit, or every 10 hours-ish, the star loses some mass, which we don't know as prior. So that's my delta M star. You can show that the mass of the disk that will accumulate over an accretion time will be the ratio between the accretion time over the recurrence time, which you can, for reasonable parameters, we don't know h over r in detail, but it's a number that's much larger than 1. So the disk has a lot more mass than the per orbit mass loss from the star. So you can, what you should have in mind is something that's like a pebble being thrown into a pond. Okay, it's like maybe a glass of water being dumped into a pond. Okay, so most of the mass is in the disk. Okay, it's like accumulation of mass here. So we think for this reason, the quiescent emission, which is from the pond of water, is powered by accretion of this disk. Okay, and that explains this quiescent emission here. What about the eruptions? This delta M star, this is the amount of mass, will eventually get circularized. You dump some water into a pond, it will circularize, will join the pond. What happened is that the star's orbit is mildly eccentric. And this energy will go into, by the time the orbit decays, let's say, this is for the aligned case, everything is in one single plane. If you go from some eccentricity 0.5 to 0 as the gas circularizes, it will release free energy. That's the circularization. If the system is inclined, of course, you have this free energy due to the inclination as well. That will also release free energy. So the logic consequence would be that there is circularization. So however the mass joins the disk, and it can release a large energy. And the efficiency you can easily estimate for a semi-major axis of 100 Rg, you can estimate the efficiency to be of order 1%. Okay, so let's see, if you have 10 to 46 ergs per flare, and you can easily estimate how much mass per orbit the star loses. It's very, very tiny amount of mass. It's not like a huge TDE where the star is destroyed in one go. You can see that it takes a huge number of orbits for the star to become completely consumed. And for that, you can estimate the mass loss rate from the star, 10 to minus 3 solar mass per year, without even knowing what happens to the star yet. Okay, this is just from the energetics, from the orbital constraints. Okay, and then we'll later on talk about, and Elliot has mentioned how do we actually produce this mass loss rate. And the flare duration in this, at the time when we were thinking about this problem, we actually don't quite know what exactly is going to happen when the stellar mass loss, the debris, is going to join the disk. We just wave our hands. I think very hand waving. I think Itai can tell us a lot more about what exactly is happening to this duration. We just say that maybe it happens. Maybe this circularization happens on a time scale that's 1 over omega, the angular frequency at the pericenter, and that could be some sort of 10% of the orbit period. But the circularization should be very fast, okay, because the mass of this newly added debris is very small compared to the disk. It can easily get incorporated into the disk very quickly. Okay, so let's look at the broadband spectrum of the system. Okay, so let's look at the persistent disk. What happens is that the star is constantly donating mass to the disk, and the mass loss rate is about 10 to minus 3 solar mass per year. Okay. So at radii smaller than RP, RP is where mass is deposited into the disk, m dot would be roughly constant. So you set up a steady state solution where you have m dot joining the disk, and in the interior you have constant m dot. You have the standard Shakura-Sunyaev spectrum for the inner disk. But for the outer disk, it's different because the mass is deposited at the radii smaller than your outer disk, at larger than RP. What happens is that the angular momentum flux is conserved because the star, the matter that's been deposited into the disk has a certain angular momentum, and that angular momentum will be carried out to the outer, towards the outer edge of the disk. So you have a constant J dot in the outer disk. And from that, you can easily do the same calculation. You can find that the spectrum is steeper. So meaning that the inner disk is the hottest part, and then going to the outer disk, the cooler part, meaning lower frequency part, will be steeper. And then the disk has an outer edge because the finite lifetime of the system. The lifetime is between 100 to 1,000 years, and you can show that when you equate the lifetime to the local viscous time, the outer disk is roughly a few times 100, a few hundred Rg. So that sets a break here. That's the solid line here. So this is the religions. Okay. So in the optical band, it's actually roughly in between these two segments. You should roughly expect something like a religions or some steeper spectrum than the standard case. So if we don't actually have this optical data because of the angular resolution, let's say the current observations that are based on arc-second angular resolution are not enough actually, because in your aperture it's all starlight. In order to get to this level of, these are, I'm showing some magnitude over here, and actually there are also could be a star cluster, so it's quite confusing of a field. If you were to take an HST image, what we can tell is that it's something like 23 mag at the typical distance of QPEs. So if you can measure the SCD, you can tell where the outer disk is, and maybe you can get this segment as well if you go to UV. And about the QPEs, we assume that it's the energy is deposited within 10% of the orbital period of the recurrence time, and that gives you a hotter spectrum, which is shown in the dotted line. So you can imagine the system switches between this state. If you only see the system in the X-ray band, it switches from this state, and during eruption, it switches to this state, and it switches back and forth. Okay. And then when it's in this state, you detect a high X-ray flux in this band. And then when you're in this state, you detect a low X-ray flux. This is the quiescent flux, and this is the eruption flux. So now it comes to what's causing the star to lose mass. Remember that the star is losing mass at 10 to minus 3 solar mass per year. What's causing that, right? Can we self-consistently solve the problem such that we can actually show this mass loss rate? So the physical situation is that if you go to the common film of the star, what happens to the star is that it experiences ram pressure. So it's going to run into the gas in the disk. Something like that, very schematic, but Philip has a full simulation as Elliot showed. So you can easily estimate what would be the ram pressure the star experiences. And this is roughly the interior pressure of the star. So the ram pressure is much, much smaller than the average pressure inside the star. So most of the star is completely unperturbed. Only in the surface layers where the pressure is comparable to the ram pressure, and that's the surface, the outermost few percent of the star will be affected by the ram pressure, whereas the interior is completely, maybe the interior 95% of the star is untouched. Well, what happened is that the shock propagates into the star, so that you can see the red part in the star, that gets shock heated, and it will expand. It will expand into and fill up its Roche slope, and then it undergoes a Roche overflow. So very rough estimates that I did from some MESA modeling roughly tells you this. You can ask me about the details of how on hell you can do a MESA modeling of a star losing mass in such a system. I mean, the key is the shock injects entropy to the outer layers, which you can add to the outer layers of a MESA model. And then you can put the Roche potential in as well, and then that causes mass loss. So there's still some uncertainty work in progress, but we can show that this level of mass loss is possible under that ramp pressure. Okay. And the star basically looks like something like this. So that's the original, maybe 95% of the star. The star looks like this because it expands and fills up its Roche lobe. That's the heliosphere. And then there may be some mass loss from the L1 and L2 point. Okay. And that will run into the disk again. So since Elliot already mentioned the origin of the orbit, I will perhaps be very brief. So Elliot was mentioning, comparing our QPE star to the stars in our Milky Way. So that's S2, which has a 16-year orbit. And this one is absolutely tiny. You cannot even draw, this orbit in this diagram here. It's so tiny. So the 1 AU away from the supermassive black hole. And then the story is that likely story, but there are many other ways perhaps. I think the AGN gas drag seems like a good story as well. But this particular case is a binary that gets tidally broken apart and then unbound and bound star. And bound star can orbit decay and produce this. So I'm gonna, this is the summary. So we have, those are the conclusions, and there's some predictions. One of the predictions at that time we didn't really think about in detail is the timing variation of such systems. So now you have a star, which is really the precise clock, and it undergoes all sorts of GR precession, and that will affect the X-ray timing. I think a talk later on by, we'll get there for the X-ray timing. Okay, so for the rest of the maybe 3 more minutes, I want to mention something else because many people are interested in jets in TDEs, going back to TDEs. After hearing all these intriguing talks, I want to mention the rates. Okay, so the observation is that the Swift 1644-like events, their rates are something like very tiny rate because they're detected far away in a distant universe. Whereas the total TDE rate is a factor of 10 to the 4 to 10 to the 5, more than the jetted rates that we see. So there's a huge discrepancy. So why on hell the jetted TDEs are so rare? And you cannot explain this with just beaming alone. Okay? You cannot have such as fine-tuned beams. So the proposal here that we put out actually very similar. We put out similar time as what Brian has already mentioned, which I think is possibly happening in the system. So imagine a star comes in, that's the star's orbit, in an inclined orbit with respect to the spin of the black hole, which is where most of the angular momentum of the system is. The spin of the black hole stays unchanged. So that's the angular momentum of the star. So the star forms, the fallback material forms a disk. And what happens, the disk will have a jet and will have a wind as well. Okay? So the entire body precesses. Okay? So this disk, which is coupled to the wind and jet, entire body precesses around this spin axis of the black hole. And what happens is that, so we did some hydro simulations, plus some analytic estimates, very similar to Adelia and Brian did on this. So we found that our conclusions are also similar, but we found that for a sufficiently large misalignment angle, when this misalignment angle is more than a few equals to roughly 2 to 3 of the jet opening angle, the jet is hydrodynamically choked. Okay. And what happens is that if you want a J1644-like event to be seen, or 22 CMC event to be seen, you require the initial star's orbit angular momentum to be nearly aligned with the spin. And you also require the observer's viewing angle to be nearly aligned with the spin. Okay, so this double alignment, which both cases happen randomly. Okay, so the star comes in a random inclination angle, and observer is located in a random inclination angle as well. So such events would require double alignment. Okay. Such double alignment you can show, but with some breakout conditions, you can show that it roughly happens for each jetted event. It happens once in 1,000 cases. Okay. So only one out of 1,000 intrinsically jetted events would actually have successful jets that will be seen by an observer. So very confusing double alignment statement. Okay. So if you correct for this, okay, out of that total ratio, you can say that 1% to 10%, so up to 10% of TDEs are intrinsically jetted. So, and these jets carry a huge amount of energy in them. So we think that there's hidden jets, and then after Bardeen-Peterson alignment, after some time, these jets can actually have delayed breakout. And that can explain maybe some of these weird radio rebrightening and cosmic ray. Last slide, I just want to show that we did hydrosimulation of a jet, a precessing jet and precessing wind. For the large inclination angle, the jet does get choked, and for small inclination angle, the jet successfully breaks out. We can talk about this in detail if you're interested. Okay, thank you.
Using my prerogative yet again. Very interesting stuff. With regards to this spreading disk, I think in my favorite nuclear transient here, GSN 069, my personal view is that this stellar-fed disk may be undergoing outbursts that are driven by instabilities, where the disk is flushing its mass and and regaining it through collisions. And in that case, there may be some changes in the inclination of the disk with time, not just the star's precession, but the disk may change. So if you have a spreading disk which inclination is varying due to warps or anything else, then this outer disk will subtend, much larger solid angle, and you could have reprocessing. So I guess my question is kind of, have you thought about that? And if we assumed a reprocessing scenario where a sizable fraction of the quiescent X-rays were re-emitted in optical, would we even have been able to detect that yet?
That's an excellent question. So Brian's point is that the disk should, in general, be warped, because the mass that's newly joined in the disk has inclined angular momentum. So we have not thought about that. I think it could have some echo. So each of these QPEs will have an echo because of the outer disk, which spans much larger radii, would be reprocessed into the optical. I don't think the observers have worked hard enough to find the optical counterparts of QPEs. But maybe they already worked extremely hard, and then they have exhausted the data, and everything is buried below noise. I think some sort of optical emission should be there in these QPEs, but it's faint and it's variable. I think it's buried below noise at this point until we dig deeper into the optical.
But presumably reprocessing might stick above the cluster, so at least we have a chance, right? Maybe.
Yeah, likely so. Yeah, if it stands out of the star cluster, which we don't know actually, a star cluster is very uncertain, different ages and different masses. I have good hope in that direction.
Okay, thanks. Elliot, and then.
Thanks, Wenbin. On the choke jet, would all this energy injection into the surrounding medium change the optical signatures or signatures at other wavelengths in a way that's detectable?
That's right. So the setup that we did here is a very simple setup. I think it's not super realistic. What we have is a jet, so a precessing body. Okay, in the precessing body frame, it's a jet with a constant wind. Okay, so in this case, the choke jet energy gets deposited into a cocoon, and we looked at the signature very roughly, and it's in the EUV, so not in the optical. So it's too hot. It's basically too much energy is deposited into the cocoon, such that it's way too hot actually to see in the optical. So you can see there is no optical emission in this system that we consider here. But it's unrealistic. Maybe we want to consider more realistic wind profile.
Maybe good for neutrinos.
Thanks.
Yeah.
Okay, nice talk, Wenbin. So I also want to ask about this model. Maybe this question goes to Brian as well. So when we do geometry simulations, we usually see the jet, at least the base of the jet, to be aligned with the black hole spin. And then far away could be affected by the orientation of the disk.
That's right.
But in case of a TDE, we expect the disk to be pretty small anyway, so probably the jet is not going to be, in the wind direction initially. So how is that going to change your picture?
That's right. Yeah, so that's a very good question. So based on the simulation by Matthew Liska, and that's where the motivation comes from. So they found that in a misaligned case, although the disk body undergoes precession, the spin axis stays unchanged. So the jet at its base is aligned with the spin, whereas the jet gets collimated by the disk body at larger scale. So here the disk is about 100 Rg in this TDE or slightly larger. So the disk has enough, force to realign the jet with the disk. That's the hypothesis here. We're assuming that the jet is realigned with the disk at larger scales.
I see.
I think in the Liska simulations aren't much larger than 100 Rg. So I think they've shown that
they have shown, that's right.
For similar dimension systems.
That's right. They have shown that they do align with the disk, the jets.
But I think in the end, it's the comeback between the power of the jet and the strength of the thickness of the disk. So if it's a very, very strong jet, so maybe that collimation distance will go a bit further.
Yeah, they have a thick disk in their simulation. So
if the jet is strong, it may also align through this MHD mechanism too. So.
Okay. Yes.
Thank you.
Richard?
Yeah, so I was just interested in the scenario where you've got your star comes in and shocks against the disk and then produces the X-rays. Isn't that going to be in a regime which is not optically thick? In which case you'd be expecting to see some emission lines in the X-rays.
It's highly optically thick.
It is.
Actually, so everything, including the disk, including all the gas that's surrounding the star, is highly optically thick. So in order for photons to get out, things have to expand. You may drive. I don't think there will be any lines really in this. It's too hot for any lines to be emitted in the X-ray band.
Well, it's not too hot, is it? Because you get oxygen at 0.6 keV or something would be. I mean, it's optically thick. You won't see it now.
Yeah, let's see what kind of lines
fine.
you could have. Let's say carbon K alpha or some. I think. Yeah, I think
more like oxygen.
There's not. I don't have much hope in detecting lines in the QPE, either quiescence or eruption. But maybe we should still try.
I don't think it's impossible you could get it in the debris, but it would be highly
oh, you mean the
Doppler
reflection?
broadened. Yeah, the collision material, but it would be highly, because the velocities would be like 10th of C or something.
Yeah, everything is, yeah, exactly. The Doppler smearing is also crazy here. But then I think the reflection can give you iron lines. But the X-rays are not high energy enough. I don't think there will be iron line, but maybe carbon K alpha line and so on. Yeah. Thank you.
Yeah, two thoughts that maybe be interested to hear what you think. So one, there should be a connection in this choke jet, processing choke jet scenario between the energy of the jet, the opening angle, and the time of breakout. So that might lead to some observational consequences. And the other point is, in those cases where we do choke the jet, the energy should eventually come out in very late radio. So
right.
We should be able to know, right? So yeah, just wanted to hear what.
That's right. Yeah, we did a different jet opening angle. It's much easier for wider jets to get out. So that's very, you can easily imagine a wider jet with this cavity is open all the time, so it does not interact with much matter along its way. So wider jets can easily get out. So observationally, nature would favor, the successful jets would favor wider ones. Okay. And then in terms of where the energy goes, it will go into an outflow. The cocoon will generate radio. So the energy, these ones, even if in the choke jet case, you should still see this wide angle outflow, which will generate radio. Will not be this rapidly rising after off-axis afterglow, but very broad light curves. Not sure if those are seen, but it looks like they should be choked.
The time scale would be very long, but the energy would be huge.
Yeah, energy will be huge. Yeah. Mm-hmm.
Yeah. Thanks.
My question is related. So it seems that even if you have very high quality radio ICDs across several years, it's still a little hard to differentiate between the outflow and the relativistic jet model. Mm-hmm. What type of radio observation do you think we should do to really test this? The proposal is that this is the initial state of the jet. Okay, and maybe initially they're 45-degree inclined,
But over time, the jet will be brought into alignment with the spin of the black hole. And that time scale, depending on the damping of the precession, is still unclear. I would say that eventually the jets should be successful after some delay. You would get some wide angle outflow, maybe 0.1 C or even higher outflow. But other than that, you should also get the jet. So the jet will be off-axis jet. So you have this late time rising, but you also have the wide angle outflow. I would say depending on the realignment time scale, maybe a larger fraction of the energy is actually in the successful jet that breaks out later. Maybe a smaller fraction of the energy is in the wide angle outflow, maybe because this may only last for a short amount of time, maybe several weeks, if it happens really efficiently. But that we don't know. I would imagine that late time for all those TDEs go late time and try to constrain if there's any late time huge radio flare at all, do a comprehensive survey of all the late time, meaning 3 years, 5 years. Because once you see the jet afterglow, it lasts for a very long time.
Okay, we will have to go, so let's thank Wenbin again.
Thank you.